So now let's consider one of the major problems that our integral calculus is aimed towards, and that is if we have a curve like this one, f of x equals 2 minus 1 half x squared on the interval from 0 to 2, we might be interested in finding out what is the area under this curve. How could we do it? Given our method so far, we haven't really got a good method unless we estimate it. So there's a couple of ways that we can approximate this area, and one might be to inscribe rectangles underneath the curve or some other shape and circumscribe, which means to write outside. And here's what that looks like. If we had rectangles that were inscribed in the rectangle, the upper part of each rectangle is only along the curve, but inside of the curve. Circumscribed, the upper corners of each of the rectangles are along the outside of the curve right here, at least in this case on the left-hand side, the upper part of the rectangle. One is going to underestimate the area, one's going to overestimate the area, but maybe by doing that kind of thing we can figure out an area in between these two to figure it out. So that's what we're going to do. Let's just work out what this would be if we had these rectangles. Now in this case we're only going to be dealing with 4 rectangles just for the ease of doing the calculation. Clearly if we had a few more rectangles it might actually be a little bit of a better estimate. But just so that we can get a feel for how this is going to work out, we'll note that if the rectangles are nice and evenly spaced right here, that the width of each one of these rectangles right here will be equal to 1/2. And so if we go along the line right here, getting our values of x at each of these 1/2 marks, then that will be our width. So the width in each one of these cases, in each one of these rectangles, is going to be a consistent width of 1/2, and that's a helpful thing. Now, in this first case of these inscribed rectangles, we're going to get the actual height by using the value of the function at these coordinate points right here. So this value right here, this height is going to be f of 1/2. This next value right here is going to be f of 1. This next value right here would be f of 1/2. That's 3/2, of course. And this last height right here would be f of 2. Now we note that f of 2, at least in this inscribed rectangle situation, is equal to 0. So that's an easy rectangle to figure out right here. Well, here's how that summation looks. And I've written this out for both the inscribed and the circumscribed situations right here. 1/2 times f of 1/2 plus 1/2 times f of 1 plus 1/2 times the function at 3/2 plus 1/2 times the function at 2, where each of the right-hand endpoints define our height, whereas in this case we start at f of 0 and end at f of 3/2 to indicate our left-hand endpoints of each of these rectangles. So now it's just a matter of substituting in the numbers 1/2, 1, 3/2, and 2, etc. into our function to figure out what's going to happen. So in this first case right here, if I factor out 1/2 from each of the terms and calculate 2 minus 1/2 of x squared in each point, I get 15/8, 3/2, 7/8, and 0 as the y values. Well, this turns out to be 17/4 right here. 1/2 of that, 17/8, as a decimal is 2.125. And so we'll repeat the same thing that we just did over on the left here in blue for our circumscribed area. Let's see what we get there. You'll notice that by evaluating the numbers at 0, 1/2, 1, and 3/2, we get the same sequence that we had in the middle here, but this time we're going to add 2, and so which is to say 1/2 times 25/4, so 25/8, which reduces as a decimal to 3.125. So according to this, our actual area should be somewhere between 2.125, which clearly left off a lot of space right here in white, and 3.125, in which we added a lot of area over here in gray. So in the next video, we'll check that out. How do we actually work this out in a general sense?